Hello, everyone. Welcome to the very first Preparing for the PAT webinar 2024. We are streaming live on YouTube, and if you want to join us over on Zoom, you will be able to access our chat features as well. My name is Kat. My pronouns are she and her. I'm the Access Officer for the Department of Physics. What that means is I run most of our programs for secondary school students, including all of our stuff to support young people like you who are interested in applying to study physics here in Oxford. This session is being recorded, and I will share the link for the recording with you tomorrow. A reminder of the housekeeping rules for those of you joining on Zoom. You will be able to use the Q&A today for any questions that you would like to be addressed. I'll let you know when it is switched on and ready, because it will not be available for the whole of today's session. You can also use chat to share your thoughts, but please keep it polite and kind. Don't share any personal details or information, so no email addresses, phone numbers, or anything like that. Keep any questions in the Q&A, otherwise we might miss them coming up and down the chat. If at any point this evening you are feeling unsafe, you are welcome to contact our safeguarding lead on safeguarding@physics.ox.ac.uk, and I'm going to type that into the chat so that if anyone has need of it, you are able to contact us nice and quickly. But with that, I'm going to switch the chat off for this section of today's event, and we're going to get started properly. Before we jump in with our problem solving this evening, I'm going to give you a very quick introduction to the Preparing for the PAT course and the PAT itself. I will not take any questions in this section because we just don't have time, but we have a webinar scheduled, our third webinar, which will be our third study focus webinar in September, and that is just for PAT logistics and your questions. So we have scheduled this into our thoughts. For now, I will repeat this quick introduction each week for new joiners to the course, and where there is time each week, I'll answer questions at the end of the webinar. First things first, the PAT is the physics admissions test at Oxford University. It must be sat by all candidates for physics, physics and philosophy, engineering, and materials science. Your result on the PAT forms part of the information which the admissions tutors use to decide who is shortlisted for interview. To sit the PAT, you will need to register yourself as a candidate. Your school will not do this for you. The PAT this year will be on screen and entirely multiple choice. We've worked really hard to make sure that we can gain as much information as possible from this format. So the answers won't just be simply 1 mark or 0 marks. We'll also have a really good idea about your working from which wrong answer you selected, and we'll have questions where you're selecting multiple answers. The online test will include a built-in on-screen calculator, which looks exactly like a regular calculator and works in the same way. It's lovely and simple. You'll have access to a practice of this test format, including the calculator, for over 2 months before the PAT. We are hoping that we will have that ready by the end of June or thereabout. There will be no exceptions. You will have to use the online calculator. Nothing else is allowed into the exam centres. The PAT prep course itself, this webinar is part of that course, and we run this course on behalf of all subjects who require the PAT. The Preparing for the PAT course is a series of 8 webinars, along with problem sets and summer assignments that we hope will provide you with all of the information you need to take the PAT, help you prepare for the PAT, and be confident going into interviews if you're shortlisted. The timetable on screen at the moment is part of the timetable which is at the bottom of every single PAT email, and it's always highlighted in yellow where we are so you can follow our progress. At the moment, we are on Study Focus 1 on the 19th of June. I shared the joining link with you on Monday, and I will share problem set 1 tomorrow morning after this session. In each session, I'll fill you in on any updates or news as we approach key dates, which brings us to where you can find out the information. So all of the information about the course and the Preparing for the PAT course and all of the course materials are on our course materials page, which you can see on screen, and I will link to in every single email. At the moment, the page looks like this. The introduction to physics problem solving has lots of general problem solving hints and tips. Our teacher who's joining us tonight will take you through this evening, but there's even more in that introduction. Then underneath, there are all the links that you need. So at the moment, you can see it's only got the problems which we're using tonight, but this page will be updated after every session and clearly labeled so that you can find everything you need. Finally, this is where all of your key information about the PAT can be found. I will share this link in every email. It's the most up-to-date page. It's the one to check first for any information that you need. It also has an FAQ page, which is really useful. Some key facts for you. All tests this year will be sat at Pearson test centres. These venues are in almost every country around the world. This will be the case for international candidates as well as UK-based candidates. And when you register, you will be able to select a test centre which is most convenient for you. For some people, this may involve some travel, but hopefully not too much. This arrangement is different to previous years for the PAT, but it's the same setup that tests like the LNAT, the Law Admissions Test, and the Medical Admissions Tests have been using for a very long time. And it's also the same test provider that Cambridge are using this year. So the majority of university admissions tests this year will be sat at Pearson test centres. Registration for the PAT will be between the 15th of August and the 4th of October 2024. So registration has not opened yet, and I will keep you informed as we get closer to the date. The test format, which I've mentioned earlier, is a new one. It's not a big change, but because the questions will be really similar and the syllabus is completely unchanged. But even though in that sense it's not a big change, we don't want anybody feeling anxious about this. And so you will be able to access a trial version of the test, including the calculator, very soon. It's not quite ready. I'll update you. We're aiming to have it available at the end of this month. And I think the only other thing to let you know is that the PAT date so far, we know it's going to be between the 21st and the 31st of October. And we hope to narrow that down to the actual date we are hosting it on by the end of this month as well. That is my quick PAT introduction and update. Hopefully it was helpful. I'll take some questions at the end of the webinar if we have time. But for now, I'm going to stop screen sharing and hand it over to Rachel for our first PAT study focus session. Hello, Rachel.
Hi, good evening, everyone.
Thank you so much for joining us, Rachel. I'm going to disappear off into the background, answer any questions that come through, and let you get started. Let me know when you want me to share links and things.
Great, thanks very much, Kat. So, good evening, everyone. I'm a physics teacher and a head of science based in West London. And I've worked with Kat for a while now on these sessions. And the first session we're looking at tonight is how to turn words into maths. So we're looking here at how to break down problems, how to start problems well, and where to make a good start and find a good direction. Okay, so what I'll do is I'll introduce you to some questions and you can work at your own pace. I will give hints. Don't worry if you're finding it hard, because some of these questions and styles of questions might be new to you, but this is all going to be good practice, because a key area of doing well in PAT questions is you're building your resilience over time, understanding how to break down questions, and practicing over this summer to improve your physics problem solving skills and mathematical problem solving skills. So a few hints for this evening. This will help at A level as well, because I'm sure you come across some tricky questions in your studies. So for the PAT, you'll need to be able to decode questions. So you need to be able to turn the English into physics and maths. If you're doing some working out on a rough piece of paper, you need for yourself to have really clear layout and working, okay, so that you don't get lost and tangled up in your own working out. Do not rush to start the question. So make sure when you've got a question in front of you, and I'll be silent at moments this evening so you can read the question thoroughly. You need to read a question at least twice if it's a lengthy question, and don't rush. Make sure you're laying out the initial values that you know. Don't rush to start the question. It's important that you think things through carefully before you start. When you're doing your rough working, underline key information. So today, make sure you've got some paper in front of you and a pen so that you can underline some key working. And a really good practice in terms of problem solving is to turn words into symbols. So you might want to use subscripts. So for example, the speed of the car, you might use VC, so velocity, or that would be an appropriate symbol to use. The weight of the passenger, you might use W subscript P. If X is twice Y, then obviously we would need to turn that into X equals 2Y. And bear in mind conservation laws. So for example, remember your momentum conservation laws, your energy conservation laws. And if a question involves particles, we always know, for example, the charge of an electron, E. So an alpha particle's charge is 2e, for example, like linking our knowledge and our constants. We'll do a question involving this tonight, but some units are equivalent. So for example, if you know accelerations in meters per second squared, we also know that that's the same value in newtons per kilogram. And that comes from Newton's second law, F equals ma, and we can derive those units. So obviously that's a more straightforward one that you've probably seen before, but we can do that with anything, and it's called dimensional analysis sometimes as well. Projectiles and SUVAC questions, in those kinds of questions, there's a lot of unsaid information. So for example, dropped means we would have an initial speed or initial velocity of 0 meters per second. So what is said in the question and what is stated and what is unsaid, if you see the word from rest, that would mean the same thing. So in problem solving, it's what is the question telling you, what clues is it actually giving? But on the other hand, don't get bogged down in any decoy data in the question. So for example, you might not always need to use the maths in part A of the question, part B of the question, but you're given it. So you might not need that value, and it's decoy data that's just available for you. Okay, so during this session, I'll be putting questions on the board, and at the moment, the chat bar is open for hosts and panelists, so I can see any answers you're putting in, any numerical answers. If you've got a question that really needs to be answered about the questions we're going through, type it into the Q&A, because then I won't miss it. So the Q&A is for a question about the questions. The chat bar is really helpful if you use that to write a numerical answer, or to write a numerical answer for the first part of the question. But in the meantime, I'm going to put the first question up. I'm going to be quiet for a moment while you read it. Okay? And also turn my video off so I can fix something on my computer. Have a read of example 1, and there's a few hints at the bottom. So it's important in this question to turn the words into symbols on your rough piece of paper. So make sure you've got a piece of paper in front of you. And remember facts like if x is twice y, we need to turn that into things like x equals 2y. So there's an assumption there that we can use. Assume you're only taking one button at a time and replacing it in the jar. And this is a probability question. So turning words and symbols, I would start the question like this. And you might use other terminology, but as long as you're clear in your own working to guide you to the answer, that's going to be really, really important. So I can see a few people putting answers when they're ready in the chat bar. That's really helpful to show me how many people are getting ready with their answers. No rush. Okay, so there we've turned in the idea. All of this first section here, there's twice as many yellow as green, twice as many red as yellow, twice as many blue as red. We've turned that into ny equals 2ng, nr equals 2ny, nb equals 2nr. So well done, loads of answers coming in. Fantastic, well done James, well done Alexander, well done Finley, well done Aletta. Okay, so I can see lots of people on the right lines. I can see we've had a bit of practice at this kind of question before. Classic probability. So an assumption, you can either solve these equations simultaneously, or sometimes for problem solving, it's more simple to make an assumption. So it might be easy to assume that we have one green button. Okay, because that is from this mathematics here, the least number of buttons we'll have of any one color. And if you assume we put one green button, we can assume the ratio is one green button, and that ny equals 2ng's, to 2 green buttons, to 4 red buttons, to 8 blue buttons. And that's because we've got twice as many red as yellow, nr equals 2ny, and then twice as many blue as red. Okay, and that's nb equals 2nr. And once we have the ratios, we then have the probabilities, because if we've assumed we've got one green button, we can assume in total and calculate we've got 15 buttons in total. And if you just want to check that assumption, you can assume any value of green button, and you will then still end up with the same probability. So well done, you can see loads of answers having come in just there. Yeah, and reading the question, that is going to be a real challenge. I've seen a comment from someone that it was the reading comprehension side. That's why I mentioned don't rush into it, okay? And really important to lay down what you know already, turn your question into maths to start off with, and then you'll be able to make some good progress after that. So really spend the time reading the question twice, okay? Really make sure you note down a good starting point and then check again with the question that that is correct. So even when I was reading things out just then, I was going back to the question, linking it back to the maths I had on the screen here. Sorry, I'm pointing at the screen just like when I'm in the classroom. Okay, so well done. We should end up with blue being 8 over 15 probability. Red is 4 over 15. Yellow is 2 over 15. And green is 1 over 15. So what I'll do is in about 30 seconds, I'll go on to the next question. But if you're wanting to just really finish that off, no problem. The next question will be on the board in about 20 seconds. And remember, if you have a specific question about a question, use the Q&A. And then both Kat and me can address it there. But answers to questions, that's really helpful for me to see it in the chat bar. But well done. Thank you so much. Great to have such great participation here. Well done, everyone. Okay, so if you're finishing that last question off, no problem. But the next question's on the board. I'll be quiet for a moment and turn my camera off and let you have a chance to read it. Okay, great to see some answers coming in. Well done. So the hints at the bottom, remember projectiles and CVAC questions, there's a lot of unsaid information in any question. And watch out for any decoy data in the question as well. There's one shortcut, so I think some of you might have found it because you got to the answer very quickly. But there are two ways through these questions. So I'll do the slightly slower route first, but you'll get there to the right answer. Have a think about which information in this question is irrelevant. So when we break down that question on your blank piece of paper, this is the kind of information you should be noting down. So the unsaid information is that the vertical acceleration, and that's why I've used the terminology AV. Remember, we're on Earth, so G, and we're going to say that downwards is negative, is minus 9.81 meters per second squared. Okay, this assumption here, the gun and the car are at the same level. That means when the projectile lands further down the track, there's no vertical displacement. Okay, so that's that assumption picked apart. And it's traveling at a speed of 100 meters per second, passes the gun just as it is fired. They're in the same frame of reference. So we're going to have the same time for them both to travel down the track. So the information that's irrelevant is mass. It's not required at all to solve this CVAT. So I did warn you there'd be some decoy information. And we don't need mass in CVAT. What's going to be really important is all the other areas of CVAT, but constant acceleration or no acceleration in this question. So we've already said the information that's hidden in the question is the vertical acceleration. Same frame of reference, same thing for both, often can help to draw a diagram. What exactly are we looking at in this setup? Because a couple of people got 30 degrees and that's not the right angle. So sometimes a diagram might be really helpful to check you're working out. And then you can see theta, the angle upwards from the horizontal that the projectile needs to be fired at. So possibly if you found 30, you maybe just resolved slightly incorrectly. So we're looking at the car and we're looking at the projectile because those are both the things that are moving. And if we go fully through the whole method, from start to finish, we could use SUVAT. Okay, and so we know for the projectile to land in the car, there's no vertical displacement from start to end, but we can ignore any vertical y components. So we're just going to think in the x component. And horizontally, we know that the car will move distance s, the mystery distance. We know the projectile will move distance s. The car starts 100 meters per second and it's going at constant speed with zero acceleration. We know the projectile has a speed of 200 meters per second, but is being fired at angle theta to the horizontal. So we're using cos when we resolve the initial speed. And again, that will be the same because it's following a projectile. If you just watch my laser, a projectile motion, that will be that same speed when it comes to land back in the car. The horizontal acceleration again of that projectile will be zero. We're assuming there's no air resistance. And time is the thing that links these elements. So if we were using S equals ut plus half at squared, we could say that S is also the thing that links these two. We know that acceleration is both. So the only thing in S equals ut plus half at squared that's important is ut equals ut. We know that the t's are the same because the projectile has to land after a certain time in the cart. So really, you're just saying that u of the car is equal to u of the projectile. So 100 is equal to 200 cos theta. And the shortcut was that in the first place, for the projectile to land back in the car, the horizontal car velocity has to be equivalent to the horizontal projectile velocity. So we assume there's no air resistance, we assume there's no horizontal acceleration. So just logically, or like using a problem-solving brain, for the two objects to both start and end at the same horizontal displacement, they must have originally been traveling at the same horizontal velocity in the first place. So well done. We've seen so many answers of 60 degrees. Well done. Too many to name check. Fantastic work. But if you got that really quickly, you maybe use the shortcut of realizing that the initial velocities had to be the same horizontally in the horizontal component. Or if you didn't spot the shortcut, you used the mathematical method and ended up with 6 degrees, well done. If you didn't end up with 60 degrees, just be careful. Firstly, is your calculator set on radians by accident? Or did you use sine instead of cos? When you draw out the triangle here, just make sure you're using your trig appropriately, labeling your sides. Have you got your opposite, adjacent hypotenuse? That's probably the other thing to check if you got 30 degrees instead. So well done. Okay, I'll move on to the next question. If you're still going through your working, that's fine. Just remember the final answer is 60 degrees. And if you have a question, put in the Q&A, or if you want me to go back to a slide later on, Q&A is probably the best place for that, okay? But to keep this moving on, I'm going to show you the third example, and I'll be quiet for a second while you're reading, and I'm looking at the questions in the Q&A. Okay, so have a good read of that. I'll be quiet a little bit longer. But the first step is to turn words into symbols. And I'd really stress, don't want to give that away too early, actually. The final part of the question is how long would it take a mauve caterpillar, going through all the shades of lilac and purple here, to crawl around the equator of Pluto? Okay, so that's the final part of the question, but this one is more lengthy than any of the questions we've done so far. So have a go at turning those 5 statements, without giving away, that's what we're heading towards, those 5 statements into equations as the first part of this, and see where you go from there. There'll be more than one route to solve this. I can check your final answer, but I'll show you my way in a moment. I had a couple of suggestions. Raza, well done. You can see if your working matches up with mine, or look at the pack that's been emailed. Yeah, and maybe for this one, Kat, we open the chat, because it could be good to see people's answers coming through and people can see each other's. Remember, if you've got a question, use a Q&A.
So hope that should be there now. Everyone should be able to reply to everyone. And hopefully now that everyone's had a few questions and is getting into the swing of it, they'll feel a bit more confident about sharing them publicly as well. You also don't have to. You can still share them with just me and Rachel if you prefer.
Yeah, if you prefer just me and Kat to see them, you can press host and panelists. So please keep participating here. Well done. Okay, so I'll show you how I turn those into maths first of all. Okay, and remember, probably go with final answers. So Alexandra and Isaac, just have another look. Finley, Emma, well done. Probably hard for me to check every line of working, so if you go with final answers. So I've turned all the 5 statements into maths here. Okay, so we've got long statements, long questions, turned all 5 statements into mathematics. And there's multiple routes through this question. You might have done something different. But this is a really fun question because it takes quite a few steps to get there, but it's really satisfying when you reach the final answer, and that's the best kind of question. Okay, so there's multiple routes. I'll show you one. Remember the end goal. Always hold that in your mind when you're problem solving. The end goal is the time for the mauve caterpillar to go around that equator, not the distance. Okay, that is not the end goal. The distance, we can actually do that in the question because we've got the radius, but the end goal is the time for the mauve caterpillar. So because you're looking for time, you need to work with velocity. And the only way we're going to get the time for the mauve caterpillar is by calculating the velocity. So we need to use this fact here, that the velocity of the mauve caterpillar is twice the velocity of the lilac caterpillar. And we also know from statement 4, so I'll keep referring to my numbers statements, which link to the statement numbers in the question. Okay. And well done, people are already noticing that they've chosen the wrong caterpillar. So that's where the subscripts in your notation are really, really important for being clear and consistent. And this is why it's good to go back and check the question and to go back and check your working as well. Okay. So I'm using statements 5 and 4 eventually, but not quite yet. And it's just a reminder that then I need to use statement 4, statement 5, because the length of the violet caterpillar over 10 will give me the velocity of the violet caterpillar. And that will help me work out the velocity of the mauve caterpillar, which I'm going to need to find out the time it takes. So I'm actually, before I start looking at 4 and 5, going to use statements 1 to 3, equations 1 to 3. And I'm going to rewrite them and make them look a little bit more uniform. You could do this another way. You could solve this simultaneously a different method. But I'm just going to remind myself that, for example, in statement 1, in equation 1, there's actually nothing to do with the length of the lilac caterpillar there. But I'm just going to put a 0 next to it. Plus 5lm minus 7lv equals 0. So you can see I've just rearranged that first equation and the second and the third in a really consistent format, always going length of the lilac, length of the mauve, length of the violet. And then it just keeps my workings really, really clear for what I'm about to do next. And what I'm about to do next is, oh, hold on, just lost my computer. Choose a term to eliminate. And so I'm going to choose length of the lilac caterpillar because it's definitely not needed later on. Nothing in this green box here is to do with the lilac caterpillar. You might have chosen a different route, but that's probably a straightforward step for me. And then I'm going to multiply equation 13 here by 5 over 3 as well, because that's going to give me a few better fractions to deal with. So I've multiplied that by 5 over 3, and that means I can eliminate the length of the lilac caterpillar if I now subtract equation 13 from equation 14. So equation 14 was this. If I subtract equation 13 and try to color code things here, so I've got equation 14, take away equation 13, I'll end up, sorry, I moved it up a bit, I must have put it again for some reason. I'll end up with an equation here for the length of the mauve caterpillar. Okay. Yeah, and remember with the radius, they've also thrown something else in, just saw a few questions in the chat bar. We're dealing with kilometers, okay? So don't forget that aspect, and it's a radius. And so we're dealing with a whole sphere here, everyone, okay? So we've got the length of the mauve caterpillar in the method that I've used. And we're now going to substitute that in to equation 1. So all of those equations are still relevant, even though I had equation back here, 12, 13, 14, I can still substitute that back into equation 1, okay? And substitute it into equation 1. That will bring me this, okay? And eventually I'll end up, because I've substituted LM into this, I end up with a value in meters for the length of the violet caterpillar. Okay, so obviously that's every step of the working shown. Okay. And then we can substitute that length of the violet caterpillar into this term here, and you can get the velocity of the mauve caterpillar. So if anyone wants me to go through any steps, probably put that in the Q&A if you want me to go back a slide. And it's really good to see a bit of debate about the answers. Sort of in my problem solving here, I'd actually accept either as the final answer for time 7.4 times 10 to the 8 or 7.2 times 10 to the 8 seconds, because one of those was done using a calculator, and one of those would have been without a calculator and making an assumption about the size of pi, rounding pi to 3, rounding the radius to 1,200 kilometers. But you will have a calculator available. It's just important to use that only in the final step of calculation. So simplifying and simplifying here. So you should find that the velocity of the mauve caterpillar is 0.01 meters per second. It's going to take quite a while for the caterpillar to crawl around the radius of Pluto. And that's where you have to remember that the question's giving you a hint at the point it mentions radius. That is not a distance. Well, I suppose in some ways it is, but that's not the distance that the mauve caterpillar is traveling. The mauve caterpillar is actually got to travel in a circle. It's got to go the circumference round the equator of Pluto. So make sure then you do have to learn your geometric equations. So we need to use the circumference. We're given the radius, so 2 pi r over Vm, and you should end up with 7.4 times 10 to the 8 seconds. Remember, if you've got questions, pop them in the Q&A, but it was really good to see so many answers coming in just then. And remember, pop any questions, or if you'd like me to go back a slide, just let me know in the Q&A. But good to see you debating a little bit between yourselves as well. Really good participation. And if you found that hard, don't worry. This is what the whole summer's for, practice, okay? So the velocity, just to go back one more step, we can only find velocity. So just had a question in the chat bar. In the Q&A, sorry. We can only get velocity if we found the length of the violet caterpillar. And I found the length of the violet caterpillar by using equations 1 to 3 and solving them simultaneously. So I can go back one more step, and just to remind that I rewrote equations 1 to 3 in this format, so a little bit more uniform in format, and then worked out that I am going to need to find the length of the violet caterpillar. The quickest route there is to know the length of the mauve caterpillar. Okay, and the reason I know I need the length of the violet caterpillar is that's what I solved for earlier when I merged equations 4 and 5, substituted them into each other, sorry, not merged. And then think about male merge. And then we have these equations rewritten as equation 12, 13, and 14. And I realized from these, the most important thing to eliminate first was the length of the violet caterpillar. I can multiply 3 by 5 over 3, because that's going to mean that I can subtract equations 13 and 14. So subtract equation 13, which is where my pointer is now, from equation 14. And that's going to really easily allow me to cancel the length of the lilac caterpillar. And that gives me a term for the length of the mauve caterpillar. There is a bit of a step of working out missing there, okay? So you make length of the mauve caterpillar, you subtract these two equations, and then you make length of the mauve caterpillar the subject. You then substitute that back in to equation 1, because that's the only equation that also has length of the mauve caterpillar and length of the violet. And then you pop that into the the velocity of the mauve caterpillar equation. When you pop that into the velocity of the mauve caterpillar equation, you get the length of the violet caterpillar being 0.05 meters. And that is with a bit of working out and algebra to get there, and substitution and fractions. And once you've got the length of the violet caterpillar, you can work out the velocity of the mauve caterpillar by substituting into this equation, and you get a velocity of 0.01 meters per second. So that's the big thing you have to be able to calculate in this question before you can work out the time it takes to crawl around the circumference. Okay? So I'll pop the next question on the board and I'll look at any questions in the Q&A. And what you can do as well, if you want to relook at a question, is Kat has popped the workbook for today's question in the chat bar. But at the moment, try not to look at the hints apart from what's on the slides, because you want to try and problem solve each of these fresh. The workbook especially will be good for looking back at a question or reviewing them afterwards. Okay? I'll be quiet while you solve this question. This is one of those questions on using the units or dimensional analysis. Okay, so well done, seen a few correct answers coming in. You're welcome to look at the next question in the workbook if you feel you have solved it. But there's a real clue in the question there. We're doing dimensional analysis here, but K is a dimensionless constant, as is often used in maths and physics. So I'm going to first of all rewrite. Hold on, sorry. Okay, first of all, rewrite the equation by adding in units. So I know as a starting point, but this might not be what we use the whole time, the units for force are newtons. K has no units, so I don't need to write an equation down here with units in, but R has units M. So I keep that power of X acting on the M, the meters, sorry, because R is, as it says in the question, it defines what R is. R is the radius of the sphere, velocity of the sphere in B, and then we've got viscosity here. Okay, coefficient of viscosity, and it gives you at the end, that new one, the units for viscosity. So always check the whole part of the question for the information that you need. So we've got the units for viscosity here, all to the power of y, and then the units for velocity here, meters per second, all to the power z. And we must be working with our powers here, can't do any fractions, otherwise we'll get in a right pickle. So, you next, because you can't see newtons on the right-hand side of the equals, that's your hint, and I kind of mentioned it at the start of the session today, to turn that into SI units, and then we can do a bit of simplification. Some of you might be using terminology with like this with square brackets. So, for example, when we've got a mass, instead of writing kilograms, we write the symbol M. But I prefer to solve these putting the units in because they are all given in the question. And as long as we're correct mathematically, we will get there. Okay, so if you're using this method, if you have to T for time instead of putting seconds, you would then add your units at the end. That's absolutely fine as well. So whichever route you're wanting to use. Okay, so when I substitute in my units for newtons, because I remember I said Newton's second law, F equals ma equation, that is the same as kilograms times meters per second squared. And the only things I've multiplied out here is I've used the powers and popped it in each of the brackets. So x is here now, kilograms to the power y, m to the power minus y, because it was -1 here. And then I've got m to the power z, s to the power of minus z, etc. Then we can really sort out the brackets a little bit, okay? And you can see here, got the powers acting on each of the terms, but I've got 1 m here, 1 meters here, and 1 meter here. Okay, I've got m to the x, m to the minus y, m to the z. So I can still simplify this further. And when I simplify it further, instead of having m to the x, m to the minus y, and m to the z, that's the same as using my rules for powers. That's the same as having m to the x plus z minus y. Sorry, I think that's a typo there. Okay. And then we've got kilograms to the y. Okay. And seconds to the minus z minus 1. We've got a kilogram term on each side, so y equals 1. Okay, so that should say kilograms to the y there. And that means, and because there's no power here, that's a 1 raised to the power 1. So that means that immediately y equals 1. Sorry, I'll fix that typo later on. Okay. Then we've got m, where m to the 1 on the left, turn that into an equation on itself. So all the powers for m, but 1 on the left-hand side is equal to x plus z minus 1 on the right-hand side. Seconds on the left-hand side to the power of -2. So I'm using all my rules and laws for powers and indices. -2 on the left is equal to minus z minus 1 on the right-hand side, because we know now that y equals 1. So it's quite easy to see that where I had y involved before, sorry, I'm just changing slides, that because I've substituted in y equals 1, that now means that z is equal to 1. And lots of you got that very quickly, so well done. And then m is equal to 1 equals x plus z minus 1, substitute in z equals 1. That then also means that x equals 1. So in the end, actually, x, z, and y are all equal to 1. And well done. That was answered really quickly by a lot of you. So clearly good at practicing with your units and this element of dimensional analysis. So pop any questions in the Q&A. Okay, and then I'll pop the next question on the slides. So there's two methods to solve this question. I'll show you both because it will be helpful for your A-level course. But great to see some people putting some answers in. And yes, work through the question. I'll give you a bit more time. But the answer is 12 days. Okay, so the key information labelled in the question and turn the words into maths. So hopefully you read through that question a couple of times. And the half-life of A, is half the half-life of B, as stated from that question. We can use some terminology like this. You might use, if you've moved on to the radioactivity part of your course already, the initial value, because the key word here is initially, the initial number of radioactive nuclei in sample A is twice as many atoms of A as of B. Sorry, okay, so there's twice as many atoms initially of A compared to B. And then the question is, at what time will the ratio of the number of atoms of A to B be reversed? So at what point will the ratio, the number of atoms A, be equivalent to half the number of B? And this is a question that links to half-life, but there's actually a quicker solution. Okay, so you might have just written down a list of numbers, but I kind of like to pop things in the heading and show my working really clearly, because it's really important to remember that we start at the initial value at time 0. Okay, I've worked in threes, so you'll see why in a second. And I've got my number of atoms of A, my number of atoms of B, and I've color-coded something for reasons you'll see in a minute. But originally I don't have any values, but I know that for Na, I have twice as many atoms of A as of B. So I'm going to put all of my data in the table, and you could just put some headings, do some ratios and solve this. But I kind of like to go in steps and just double check my working. So I've got twice as many atoms of A than as of B. So originally I've got twice the number of B. And obviously for B, I just have that number. My original number, initial BO, that's why it's the initial value. Because the half-life of sample B is 6 days, after 6 days, I will have half the original value, NBO over 2. But the half-life of A is 3 days. So after one half-life, I'll have NBO, and that will half again here to NBO over 2. I'm halving this value here. So if the question was, when will you have the same amount, the same number of atoms? That would be after 6 days. But we're not there yet. The question wants the ratio to be reversed. So the final step, as many of you found, and that's why I've already got 12 there. Obviously, I wouldn't pre-write the number 12 unless I knew we were heading there. After another 3 days, sample A, at 9 days, that value will half again, and I'll have a quarter of what I originally had of sample B. It will half again at 12 days, and I'll have an eighth of the original value of sample B. And after 12 days here for sample B, this value at 6 days will half to sample 4. Obviously, there'll be some values in between. I'll show you some equations for a second where you could work that out. But we're looking for a ratio here, and I can see then the number atoms I have of atom A is actually half the value I have in this column here. So you might just have done some values running down the page, but what this shows us is that we have achieved this ratio, the ratio of the number of atoms of A to B being reversed, where the number of atoms of atom A is now half the number of atoms of atom B, but it's half the number here, not the original value. That's the harder part of this question. So I'm using the terminology, the initial value I should be saying. I'm using the terminology 0 to signpost my initial value of how many I had, but it's this ratio of the ratio at this point here, NA compared to NB. I'll show you quickly. Yay, and someone's just asked you a question, I'll answer verbally. Thanks, Abdul. You could definitely work using NA rather than NB, and I'm sure you found the same solution. So if you did your solution the other way around, but got 12 days, absolutely. I don't know, I just lean towards that route today. So as you'll see in problem solving, there's more than one route to the correct answer, and sometimes it's taking the first steps that's the hardest part of the question. And the hardest thing here is the turning the words into maths, sorry. When the question says initially in the sample, there's twice as many atoms of A than of B. So you've got more, the way to always think about that, you've got more of atoms A than of B. So the number of atoms I have of atom A is twice the number of atoms I have of B. That's the hard first part of the question, turning the words into maths. Okay. 9 days, good question, actually. 9 days is not an acceptable answer. We'd have to do a bit more maths to prove it, but you don't know the value in the method I've used here of the number of atoms of isotope B that you have. There, I can show you an equation in a second that you can calculate it, but then when you check that in that ratio, 9 days would not be a correct answer. So thanks for asking. I'll show you one more method. So if you have studied anything about radioactivity, or maybe you might have brushed on this at A-level, you can use A-level formula to solve this. So you can, because we're looking at a decay curve here, if you've learned about this yet, but you will do soon, that's where it's really important in general to check the PAT syllabus, because exponential, we're going to use a couple of exponential rules for this method, and it's a bit more complicated, but you do need to know your exponential and log rules for the PAT. It's in the syllabus, and you need to learn equations and things. So I thought I'd show you this one in case you've studied radioactivity, and I'm going to use some equations that are on the A-level formula sheet, just because it's a different way to solve it. So you have this equation, these equations, where the number of radioactive nuclei at any point in time depends on the number you initially had, and then you've got this exponential term, which uses this term called the decay constant, and we've got any point in time. So that's T for time. So basically, if you want to know how many nuclei of an isotope that are radioactive you have at any point in time, it depends on the initial number you had, the exponential decay curve with this value called the decay constant, and the point in time that you want to know at. So if you wanted to know at 9 days, obviously you probably have to, at 9 days, you would be able to find that value out, okay? So I'll show you a quick route here and how we can turn the words into maths again. If you've learned about decay constants, I'm not going to go into loads of detail right now, but if you know the half-life of A is half the half-life of B, then you can turn that into an equation, because the decay constant of A, therefore, is twice the size of the decay constant of B. You could also write that the other way around. So the decay constant of B is equal to the decay constant of A over 2. We already talked about that last time, the two things that I just put on the equation. But we're going to start by using Na and substitute that in. So instead of Na, we're substituting in our new exponential equation from the A-level physics formula sheet onto the left-hand side of the equation. We've got an equation now for Nb using my exponential equation for Nb into this ratio. We then can substitute in the start point of the initial ratio of the radioactive nuclei and substitute, it doesn't matter which way you substitute it in, because substitute it on the right-hand side, but I'm going to substitute this term on the left-hand side of the equation. So now we've got everything in terms of the number of initial radioactive atoms in isotope B on the left-hand side and the right-hand side. Now, obviously, because they're there on both sides, I'm not going to do it yet, actually. I'll do that in a second. And I can also substitute this idea of the decay constant, which is the new idea of the ratios, onto the left-hand side. So instead of the decay constant in terms of A, I'm just going to have everything in terms of B. And then a fraction is not going to help me, so I multiply both sides by 2 to cancel this 2 down here. And this is the step I was going for earlier. You can cancel both of these ends. They're both in terms of the initial number of B. And we have a much simpler equation than what we started off with. 2 exponential. Okay, and remember the blue box and the green box are separate. They are to do with the question. This is the goal. At what time will the ratio of the number of atoms for A to B be reversed? And this is the initial status of that ratio. Initially in the sample, there are twice as many atoms of A as of B. So what we can do then is use our mathematics and take logs of each side. So that's the term I just showed you. We can take natural logs of both sides. And we might want to end up using some log rules. So I've just popped them up there while we're practicing. Those are the sort of generic log rules. So I can rewrite this because I have natural log of 4, ln 4, but then my exponential sort of cancels or goes away, and I end up with this constant coming down, so minus 2 lambda t, and this is just a new constant minus lambda b t. And then we end up being able to find that the time that it could take is ln 4 over lambda b. There's one more equation, so you can see this method is a lot longer, but you could use it because you will get to the right answer. That the half-life, this is another equation on the A-level formula sheet, for any radioactive isotope is ln 2 over its decay constant. So that is a classic equation on the A-level formula sheet. So if you use that, I've just said that the time is going to be this answer, but I don't know what the decay constant is. You can then find the decay constant by doing ln t2 over the half-life, t half. I do know the half-life because it's in the question for isotope B. The half-life for B is 6 days. So you'll end up, if you substitute in the decay constant equation, decay probability, you can find that you'll have ln 4 over ln 2, which is something you can calculate. And you'll end up with 2 times the half-life, which is 6 days, and you end up with 12 days. But as you can see, that was a lot longer. So problem solving and breaking down the question to simplify and solving algebraically using these exponential equations is another route. Okay, so I'll put the next question on the board, and this will be our final question for this evening. And here's the final question. And I really enjoy that some people are putting their answers already. If you keep a few answers just coming to host and panelists, perhaps, but can you give me a mathematical reason why? And I'll just pop a clue on the slide. No one's given me a mathematical reason why yet. Oh, well done. Someone's mentioned uncertainty. So do you think of percentage error or percentage uncertainty in this question? And I think definitely a goal of this question is finding the actual percentage uncertainty or percentage deviation of each of the snooker ball and the Earth. So well done. I've been given some percentages on the screen.
Rachel, we've just got a few questions about the previous question while people are working this one out. I wonder if you'd be able just to very quickly cover those two questions, and that'll give people a bit more thinking time as well.
Yeah, great. Thank you,
Thank
Kat.
you.
Just reading them now. So if you're working through this question, just working off the slides, maybe take a photo of it for a second. In about 5 seconds, I'll just go back. Okay, I'm just heading back now. Abdul, I might need you to re-clarify the question. Maybe send me another one. Was it about the radioactive sample? I'll just re-explain. I think George's question is about the blue box and the green box. The blue box is the initial information you're given in the question. Okay, I'll clarify that in a sec. Thank you so much. The blue box is initially in the sample, there are twice as many of atoms of A as of B. So you've got, compared A to B, you have twice the number, the ratio of A to B, you've got double B compared to A. So that's where the blue box comes from. Okay. And then for the green box, that's your goal. That's the way I like to think about it. That's your end goal. Sporting background here. That's the goal of the question. Okay. So at what time? So you have to find how much time, the question's about days, will the ratio of number of atoms of A to B be reversed? So at what point, instead of having twice as many atoms of A compared to B, which is your starting point of the question, the blue box, which I'm highlighting with my laser pointer, when will you get to your green goal, which is Na equals Nb over 2? Okay, so the steps I did in the simpler method, which I honestly would encourage because you can use sort of ratios and it's kind of trial and error approach really, is using this starting point here where the original value, the original number of the number of initial atoms of isotope A is 2 times the number of original atoms of isotope B. And that's what I've popped in the table there. You could just write a list, that would also be fine, but I like making it neat, putting it in a table. So originally, for the number of atoms of A at time 0, I have twice the number of B, and obviously for the number of atoms B, I do just have NB0. Okay. Remember to pop questions in the Q&A so we don't miss them. After 3 days, only one of those will halve. I don't know this value here right now unless I use exponentials, so I'm just not going to fill that in, just leaving it blank. But that number halves just to NB because the half-life of isotope A is 3 days, and that's in the question. That value there, that mystery number, will half again. That's why I've written over 2. After another 3 days, and that will half again. That's why I've written a quarter, because I'm halving a half. And then I'll half a quarter, which gives me an 1/8. And I could keep going, and then I could double check this column overhead. That would be fine. I could keep going. Okay? So I could end up with a 16th. And I could go further every 3 days. But with NB, the half-life is 6 days. So I'm just going to skip down to here. It's kind of a clue that these numbers are going to work in terms of ratios, because obviously you've got 3 days and 6 days. That's a little clue as well. And only after 6 days do I have half my original value. And only after 12 days do I have a quarter. And the thing I've noticed there is that a quarter, actually maybe it's easier if I say it this way around, an 1/8 is half the size of a quarter. So the number of atoms of atom A, that's my goal that I've reached, is half, at this point, is half the number of atoms of isotope B. So that's why I've rewritten the goal. I've achieved it at 12 days because I've compared those two values, and I can see that an 1/8 is half the size of a quarter. So I'm always making that comparison. So if you have another question, just pop that in the chat, but hopefully that's shown again. The green was because it says at what time will the ratio of the number of atoms of A to B be reversed? So we're reversing that ratio. I could have also written instead, actually, maybe you would have preferred this, NB equals 2Na. That would be the same thing in this green box. So NB equals 2Na. That would be the same thing. Okay. So I'll pop back to the question. Loads of answers coming in. And if you've got any more questions, pop them in the Q&A. Sorry, I've got to skip through quite a lot of slides here. Here we go. So percentage error of this question, and make sure also you convert between millimeters, centimeters, meters, and kilometers, because there's loads of different units. So watch out for your units in any problem solving, and make sure when you're writing on a rough sheet of paper that you are noting what units and conversions you're working in, because you don't want to miss that out while you're doing some rough working, or whether you're working with the calculator. Okay, so which is smoother? So as a fraction of the Earth's radius are Mount Everest's height. So we know Mount Everest is in one particular position. And as a percentage of the Earth's radius, Mount Everest is a deviation from that radius. We could see it as an uncertainty. It's particularly high, the highest mountain on Earth. And as a percentage of the Earth's radius, its percentage is shown on the screen. For the snooker ball, you're given sort of the manufacturer's uncertainty or tolerance on the manufacture of the snooker ball, and you're given the uncertainty in millimeters, but the diameter of the snooker ball is in centimeters. But they've given you the uncertainty on that value. So again, it's just a percentage question, percentage uncertainty question. So now for the snooker ball, the percentage is 0.245%. So quite a fun question, because the Earth is technically smoother using this data and comparison. So Mount Everest is the biggest deviation on Earth, but still that's a much smaller fraction compared to the manufacturer's tolerance on the diameter measurement on the snooker. So the Earth is smoother than a snooker ball. And quite a fun question is, if the snooker ball was enlarged to the size of the Earth, can you calculate the height of the highest mountain above the radius? And it doesn't matter that we're using diameter for the snooker ball and radius for the Earth, because we know that Mount Everest is in one position, and we're given the radius in the question, and so Mount Everest would be adding, we know it's adding an extra distance on top of that radius. The question doesn't give you any other information about ocean trenches or anything. So you just got to roll with the information in the question, the data given, being really careful with the units. And we're assuming that the rest of the Earth is pretty flat compared to Mount Everest. So some good answers coming in. You can see how much higher tallest mountain would be if we actually enlarge a snooker ball to the size of the Earth, because I think most of you are getting the right answer. Yeah, we are looking at over 15,000 meters, which is a lot larger than Mount Everest, given that is our tallest mountain. Okay, so well done. When you use the percentage uncertainty of 0.245% of the snooker ball and compare that to the radius of Earth, if the snooker ball was enlarged to the size of the Earth, our highest mountain would almost double, approximately, I can make that approximation, to 15,640 meters, nearly twice the height of Mount Everest. Okay, so a few final hints and tips. Remember, you've got to decode those questions. Be really clear with your layout and working, so that when you're trying to solve the questions, you don't get lost in your own working out. That's why it's really important to try every problem-solving question without looking at any hints or tips, but with a blank sheet of paper in front of you, because you will be in a pressurized situation by the time you get to October. But that's what all of this summer is about, to make sure you have the time to practice now. So make sure you do use it. Do not rush to start the questions. Some of you noticed, and I hope you learned a little bit along the way, that if you rush into the question, you miss something. Okay, so start it by all means, but go back and reread the question again. Reread your working out as well. Underline key information in your own working out, okay, to make sure you've not missed anything. And make sure you do turn words and symbols really consistently. Okay, so I might hand over to Kat. If there's questions about the session, I'll try and answer them in the Q&A. But good luck with the next problems.
Thank you so much, Rachel. Just before you disappear, we've got a few questions about that particular problem. So we've had a few people asking, does it matter that the snooker ball, they're given the diameter, not the radius? And somebody just asking if you could repeat that answer.
Great. Thanks so much, everyone. Thanks, Kat. How's the Q&A?
No problem.
So, with percentage uncertainty and percentage difference, you can always compare percentages to each other. So I would not be able to, let's say I knew the uncertainty of the snooker ball. I had one uncertainty that was the uncertainty on, what's the best way to put this? One value of uncertainty that was the uncertainty on the radius, but one value of the uncertainty or quantity of the uncertainty that was the uncertainty on the diameter. I can't really compare those values, but if I turned each of them into a percentage, they're then comparable because it's an uncertainty that you can compare with each other. It's a little bit like if you've studied resistivity this year, you can't compare the uncertainty in your length measurement to your uncertainty in your radius measurement, but that's why you turn them into percentages, and then you can make a comparison and think about how they contribute to your percentage uncertainty and your resistivity. Okay, percentages are the only thing we can compare, so it doesn't matter that in that question, one of the parts of the question was about the radius and the tallest mountain. Like, we know the mountain is not going to be on both sides of the earth at the same time. It's just adding that extra height to one side of the earth. And then with the diameter, that's the uncertainty given by the manufacturer on that value for the diameter. So that will give us the percentage uncertainty on the diameter, the comparison of those two values. And it's a percentage uncertainty in the measurement. Also, if you scaled it up, it wouldn't make a huge difference in your final answer as well, I think. So percentage, we are always trying to make a comparison. It doesn't, if you've got your value, your measurement, and it is that uncertainty on that measurement, you can then compare them to each other regardless.
Great. Thank you so much, Rachel. We've also had a comment that I just want to expand on because I think it's such an interesting point, where someone said, for smoothness, shouldn't we be considering the number of deformities in a surface area? Which I thought was really interesting because it's a completely different way of thinking about smoothness.
Absolutely. How many deviations do you have across the whole surface? What's the spacing on them? I suppose a little bit like a diffraction grating or something.
Yeah. I think this question very much leads you to the method we've gone through here, which is how spiky rather than how many spikes. I just thought that was really
What's
interesting.
the most extreme spike there is on it?
Yeah, I just thought that was really interesting. So thank you so much for going back. And that's a little bit of a chat on percentage uncertainty for everyone. What I'm going to do, Rachel, is thank you so much for finishing in time, because I've been answering questions about the PAT format the whole time you've been talking this afternoon. And what I'm going to do now for everyone is just summarize the types of questions that I've been asking and answering today, and give you a little bit more feedback. Rachel, you are more than welcome to switch off your camera. If you wouldn't mind hanging around, though, what I'll say is, if anyone has any questions for Rachel about the problems that we've been looking at tonight, she'll be here for just another minute or two before she heads off. But I will let Rachel go off camera and take a break. And I will come on camera now to talk just a little bit about the PAT in general. But thank you so much, Rachel. It's always great working with you. So thank you so much, everyone. I want to now just summarize a few of the things that have been coming up while you've been asking things today. So about the PAT. You can sit the PAT anywhere in the world. Our Pat Pearson centres are international. When you register for the Pat, you will be able to select a test centre which is closest to you. And registration will be between the 15th of August and the 4th of October. Really importantly, when you register for the Pat, you will also be able to say that you have access requirements. So that means if you're usually in a situation where you have extra time, for example, or if you need an enlarged paper, if you have visual impairments, all these kind of things, you can apply for access arrangements at the same time as you register for the Pat. We are just in the process of finalising what kind of evidence that we will need for you. But at the moment, the important thing is that you can get access arrangements as you register. The other important thing I want to talk to you about is what is on the Pat. So we have our very own Pat syllabus. I shared the link earlier and I will share it again in tomorrow's email. So I'm not going to pop it up again just now, but I will share the link with you tomorrow. You will need to look through the Pat syllabus and you will need to do some self-study. Everyone will have topics that have not been covered in your regular school course. And that is because we have people from all over the world who sit the Pat test. So we will have people studying for International Baccalaureate, we'll have people studying for A-levels, advanced hires, SATs in America, AP courses, all kinds of courses around the world. Everyone has to look at the syllabus and you are responsible for doing the self-study required to bring you up to speed. In tandem with that, there is not a Pat formula sheet. You will need to memorize any equations which you think will be useful to you. And we very much leave that to your decision, but that's what the webinars are for, so that we're not abandoning you completely. We can point you in the right direction for all of these things and give you some real insight into the problem solving. I've then also had lots of questions about how on earth are we going to mark multiple choice? And that is a really sensible thing to be asking us. What I want you to know is that we're thinking really hard about this and we're making sure that the answers you select are not just one right answer and then we've shoved a load of random wrong answers in. Usually when we mark the Pat in previous years and we've gone through everybody's answers, the answers we get don't actually vary that much because people tend to follow roughly the same trains of thought. So what we've done this year when we're putting together our wrong answers for the multiple choice is we've worked through what we think the typical trains of thought are going to be. And that means that every answer on the Pat is a meaningful answer. There are no obvious wrongs and obvious rights. And when you select those, not the answer that we were looking for, answers, we're going to have a really good idea of what your thought process was. So we're actually going to get an awful lot of information from your multiple choice answers. Our answers are not just going to be 1 mark or 0. They are going to be graded. So some answers will be worth more than others. I cannot tell you at the moment exactly how many marks it's going to be and exactly how many questions it's going to be. What I can tell you is that we're keeping the syllabus absolutely the same, and we're aiming for it actually to feel really similar to the previous Pats. The only difference is when you get to the final answer and on paper you would have underlined it, you've now got to click which one it is. That's the only difference. In terms of being in the exam room, you will have access to a whiteboard and a pen, a physical whiteboard and pen, so that you can do all your working in exactly the same way as you would and just select your answer at the top. We won't have access to that. We will only get your answers. They will be automatically submitted to us. There'll be no extra process that you need to go through. And the standard of the Pat is going to stay where it was, which is pretty high. So we are aiming at A level and a little bit above. This is in comparison to the Cambridge test this year, which is being aimed at sort of GCSE AS level. Worth noting that one is also multiple choice this year. So I think hopefully that should give you a little bit of an insight into what it's going to look like. Straight away, loads of people like, but I don't want a whiteboard, I want paper. Unfortunately, it will be a whiteboard format. So Pearson have told us what is allowed in the exam. So it will be a whiteboard just to keep it absolutely the same for everyone. The PAT is only the admissions test for Oxford. It is not valid for any other university. So it's not like the LNAT, which is the law exam for every single university where you want to study law. The PAT is only valid for the Oxford admissions test. Likewise, the Cambridge admissions test that I just mentioned in passing, Cambridge have admissions tests as well. Their papers are all online and multiple choice this year as well. They're also being administered by Pearson test centres, and they are aiming their paper at GCSE AS level, whereas our paper is staying with the same syllabus we've had before and is quite a high level, because this is going to allow us to compare how this year's PAT went to previous PAT years. So we're keeping as many things the same as we possibly can. Okay. In terms of if you go over the pages on the whiteboard, try to write small, try to keep key information where you can. Might be worth getting hold of a whiteboard and practicing. Top tip, if you don't have a whiteboard, but you've got one of those plastic wallets, you can just shove a piece of white paper inside the plastic wallet and then use the plastic wallet as a whiteboard. It works like an absolute charm. So you don't need to go and buy expensive equipment or anything like that. Just before we finish up, let's see if there's anything else, because I think I've managed to cover most of what people have been asking. The online calculator is the only calculator allowed. Okay, we are not permitting anyone to take any other equipment into the exam. Now, I am going to finish up for tonight, but please do not worry if I have not got to your question tonight. We just have limited time every week, but we do have 8 webinars to get through. And our first webinar in September is specifically all about your questions. It's about the practicalities of the PAT, what it's going to look like in those exam centres, and all of your admissions questions. So if I haven't got to you tonight, I will get to you at some point, and definitely in that final webinar. But for now, that is the end of our first PAT webinar. I will share all sorts of information with you tomorrow. I'll share the recording, I'll share all of the links, and I will share your first problem set. But for now, thank you very much, everybody. Have a lovely evening, and I'll see you next week.